Okay, our next section is 31.2. And for this section, we need to remember certain things, and I'm going to write them down from this other page so we have them here at the top of the page. We found that we tried Q equals A e to the alpha t plus b. In the equation, L d second Q dt squared plus R dq dt plus 1 over c q is equal to 0. Because we have to solve this homogeneous equation in order to solve it in the inhomogeneous case, where this is not 0. And we found that Q is equal to this if alpha is equal to minus gamma plus or minus the square root of gamma squared minus omega naught squared, and B is equal to V times C. If there's a V over here, there is no V, so we don't have a B here that's present because there's no V, so this term is 0 in this particular case. So we only have this term to worry about with no B. And we had two definitions. The first definition was gamma, and gamma was defined as, and this is a definition, R over 2L I'll put up here a V. If we wanted to use it, then we'd get this VC part here. And omega naught squared, which is 1 over LC. That's the definition also. So this is where we were last time. And now, anytime we have a case where we have a square root, like the second order, the quadratic equation, leads us to a situation where this can be greater than this, it can be equal to this, or it can be less than this. So there are three cases. The first of these is the case where the motion is overdamped. If the motion is overdamped, then we get Q is equal to, remember we've got either a plus or a minus here. So we've got to substitute both of those in for alpha. So we have an A plus, for example. That would be, I used B and A and B in my notes, so I should probably use that again. E to the minus gamma plus the square root of gamma squared minus omega naught squared. All of this times T. Plus another constant times the other solution. Any linear combination of these two solutions will work. Again, e to the minus gamma minus the square root of gamma squared minus omega naught squared. All of that times t. And the sum of those two exponentials is going to be our solution. Now you'll notice here that there is an e to the minus gamma t in both terms. So we could factor that out and say, okay, what we have here is e to the minus gamma t times two terms, a e to the square root of all of this times t, plus b e to the minus square root times all of this. Well, it turns out that this term right here, although it looks like a positive increasing exponential, which it is always multiplied by e to the minus gamma t. And this is always smaller than gamma, which means this term is dominant. Gamma is always going to be greater than the square root of gamma squared minus omega naught squared. So this whole term is e to the minus something times t. So this decreases with time, and this decreases exponentially with time. So what we have as our solution are a combination of two terms, both of which are decreasing exponentially, as e to the minus something times t. And both of these decrease, and this is called the overdamped case. Overdamped case is where gamma is greater than omega naught. This is, for example, if you had a pendulum swinging and it were very rusty, and as the pendulum were trying to swing, here's the pendulum, and as it's trying to swing, it's got so much friction to it. In other words, friction is this term gamma. Why is that? Well, you remember gamma is equal to R over 2L, so gamma is your friction term. This term is very, very large. We're really saying that gamma dominates the oscillation or motion. So it's just going to exponentially get closer and closer and closer and never quite get there with this exponential curve here. It's got so much, like if you had this in an incredibly dense fluid, like some really thick molasses, and this thing were trying to swing back, but the molasses was just so viscous that it couldn't swing much. And so that'd be the situation we'd be faced with. The next case is what is called the critically damped. The critically damped case is where gamma is equal to omega naught. And in that particular case, you'll notice that this term, gamma squared minus omega naught squared, vanishes altogether. So we end up with just an e to the minus gamma times t. So we have our solution Q is equal to a e to the minus gamma t. Just that. Because this is 0 right here, this is 0 right here. So both of those are that's just a constant times the front. Well, it's a second order equation, so you have to have two solutions. And it turns out that you can always multiply a solution by the factor t to get another solution, and here it'd be independent. So b times t e to the minus gamma t is also a solution. In this case, called the critically damped case, this is where the friction is the least it can be, but to prevent it from swinging through. So as we decrease this term gamma, in other words, decrease the resistance, you get smaller and smaller resistance, less and less viscous fluid. Then gamma gets smaller and smaller until it swings really fast, but really never gets more than closing. So this will close. This is the solution that we have for critically damped. This is the solution we have for the overdamped. I should put a box around that, where that square root means square root of gamma squared minus omega naught squared. And looking back over the notes here, you can see that in this section we talk about the overdamped solution, which I've written out, and the critically damped solution. That's also called the degenerate case. And now we have an underdamped solution, and that's where it really gets kind of messy and a little bit more mathematically difficult, though it can be managed pretty well. We'll see. That will be in the next section.